Hello physics students, welcome to the second video in our gravity section, and in this case we're going to look at an application of gravity that had significant influence on our understanding of the world. In the previous video we just had a quick look at gravity and how we measured it, and a quick little introduction, and now we're going to look at something that all those physicists with those gravity meters managed to work out that has changed our understanding of how the Earth works. And it's gravity evidence for a process called plate tectonics, which you may have been introduced to in high school, and if you didn't, it's a shame on your education because it's a major understanding of how the Earth works. Now, this is a little GIF that rotates around. What physicists were doing, or physicists that were with gravity meters were doing, is they were taking those gravity meters everywhere and measuring the Earth's gravitational field, or the field strength at the surface of the Earth, or the surface of the ocean, etc. And those physicists often have their own specific branch of science, and we call them geophysicists because they're looking at the geology of the Earth. And this is a little GIF that shows the variation in gravity across the seafloor, because it's relatively easy to put a gravity meter on a boat and sail around the ocean and locate where you are and measure the gravity. And you can see that it varies, and there's these sort of funny lines along the ocean that these geophysicists were noting, and no one really had an explanation. It was before people could actually go down that deep enough to look at some of these things, and it was a mystery. Then they started mapping the whole surface of the Earth, so they started combining all their data together, and they found that there was big gravity spikes along, this is the Pacific Ocean, and this is North America, South America, and they noticed in the ocean there was a big gravity anomaly along the edge of the continents, and then there was also a big gravity anomaly inside the continents, just on the edge, and that happens in a number of places around the world. This is around Japan up here. There's Australia there if you're interested, and so there's another one just there at Indonesia, and some weird things happening in India. No, that's India. This is the Middle East, and so people wanted explanations for that, as scientists do, and they started even looking deeper. So what they could do is they could subtract the surface, the geology due to the Earth's crust, because they could make a best estimate of what the geology of the Earth's crust was. Then they could estimate the gravity. Then they could subtract that gravity due to the crust from their overall readings. And then they started mapping the gravity in the mantle, and they noticed that there's an anomaly going along. Again, the North America, South America on the Pacific side, and over here, and wherever there was a gravity anomaly before, there was things happening, and along these ridges that were in the middle of oceans. And so eventually people had the idea of basically plate tectonics, and that is that the Earth is made up of plates, or the Earth's crust is made up of plates, and these plates are fairly rigid. They're hard rocks. They're fairly thick, varying between I think it's about 12 kilometers and about 40 kilometers in places, and that rigid crust then sits on a molten mantle, and the mantle convects, and it convects because of the heat generated in the core and within itself due to the radioactive decay of isotopes, and that convection causes a drag effect on the rigid plates, and the rigid plates break and move around the crust. But basically, if the plates are moving, there must be a plate section where the plate is being consumed, and that's what we would have here, and a section of the plate which is being made new. And we could tell that excuse me, we can map these plates out now on the Earth, and Australia sits in the middle of a plate, and around that plate are zones of where the Australian plate is either being consumed by going underneath another plate, and in those areas you get lots of volcanoes and earthquakes. So that's Java and New Guinea and the Pacific Islands here, and New Zealand is just on the tip of one. Or there's areas on the edge of the plate where new crust is being formed, and in the Australian plate that's a mid-ocean ridge that happens between Australia and Antarctica. And so new crust is being formed in these mid-ocean ridges, and old crust is being consumed in these subduction plates. And it explains everything that happens on Earth in terms of major geological features. It's why there's volcanoes around this area, why there's earthquakes in certain areas. It explains how Africa, which used to be up against North America and South America and Australia and India, moved away from each other. It explains everything that's happened in terms of the continents over the last 13 billion years. And it wasn't just gravity evidence that did it. What also helped was people started taking ages of these rocks in the ocean, and they discovered that the rocks, they couldn't find rocks older than about 30 million years, even though we know that the Earth's a lot older than that. And so if there's no rocks on the ocean floor that's older than 30 million years, where's all the old crust gone? And so they had to have an explanation for that. And the other thing, I think I've got a slide coming up. Let's just see if I have. No. The other thing that they had, I think I talk about it some more when we do magnetism, is that they mapped out the magnetic pole reversals in these oceanic rocks, and they discovered that they were symmetrical around these lines of expansion. And we'll talk more about that when we do magnetic fields. So basically the principle of plate tectonics is your continent's a big thick crust that's made up of all the rocks that you see every day, and they move around the surface of the Earth very slowly, of course. Australia's moving towards Indonesia at about the same rate that the fingernail grows every year. So it's a slow process, but in geology terms that's okay because we've got plenty of time. And oceanic crust is consumed underneath continental crust, and it produces all these magmas. This stuff goes down into the magma and melts and gets recycled, and new oceanic crust is then formed from the mantle rocks. And so this would be new rock, and as we go this way it gets older and older, and then eventually it gets consumed in what's called a subduction zone. That's the basics of plate tectonics. And the evidence for this is pretty comprehensive. You can actually, this is present, you can actually fit the continents back together. If you go back 200 and something million years to the earliest continents, which was Pangaea, and then you had Gondwana land, which you may have heard. Actually, it should be Gondwana. And you can see that if you look at the geology, there's Australia, I think. Yeah, there's Australia, there's Antarctica, there's India, there's Africa, and there's South America. And they fit well, and the geology goes all across that. And this slow process of the continents moving apart left us with our current arrangement. And it's fairly interesting. Oh yeah, there's Gondwana. And the geology and the fossils and all, there's so much evidence, it's irrefutable that these guys were all joined together many years ago. And so plate tectonics explains that. There were alternative theories. One of the most interesting alternative theories was people accepted that all the continents joined together, but what they said was that the Earth was a lot smaller. And so the Earth expanded. It was the expanding Earth theory, and as it expanded, all the continents moved further and further away from each other. There was actually a famous Tasmanian professor that had found all this evidence for expanding Earth theory, and then when plate tectonics came out in the 1970s, so it's a relatively new concept, and it shook up all the geology and geophysics. This Tasmanian professor just wouldn't change his ideas. He was so set in it that he argued against plate tectonics until his retirement, which is a shame, because as a scientist you should be open to new ideas, and even if you've been working on something all your life, if something comes along that explains it and is simple and all the evidence is accounted for by it, you should accept it. That's how science works. Now, physicists have got better and better at mapping the Earth's gravity, and they can measure it to different levels of accuracy. And this little diagram shows you what the Earth looks like at various decimal places, and it's a little bit exaggerated, but basically if we assume that gravity is 9.8, it's a pretty smooth surface. Everywhere on the Earth is 9.8. But then as we start moving down, the Earth's the flattening and the rotation of the Earth, it's no longer a perfect sphere because it's spinning, and that varies the second decimal place. And then mountains and ocean affects the third decimal place. Internal mass distribution, so it's what's happening in the mantle, that affects the fourth decimal place. And then big reservoirs, so if you've got oil or gas and you've got water, they can affect the fifth decimal place. Earth and the ocean tides, they affect that decimal place, and finally nearby buildings affects that decimal place. And so if you're trying to measure gravity very sensitively, things like buildings and trains going past can really upset your measurements, and physicists have to take all that into consideration and find ways to solve it. But they are interested in measuring gravity way down to those decimal places. And one of the ways that they do it is they send up satellites with gravity meters on them, which fly around. And the satellites that have been measuring gravity meters, or have been measuring gravity, have got more and more sophisticated through the years. And this little diagram just shows you how the variation, what they've done is they distort the Earth's shape according to gravity. And this one, the GOSI, is measuring it with much more accuracy than previous ones. This guy, I think, is still flying around, but it's now been turned off, basically. It did its job and then was turned off. So in the next video we're actually going to start the physics. That's enough introduction and a little bit of flavour. Let's start actually learning some of the equations that we have to do. Alright, cheerio!